Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we are in this module we will be starting our discussion on the concept of stable equilibrium and the small oscillations about that equilibrium. Okay, so stable equilibrium and small oscillations about that equilibrium. So to begin with, let us define what do we mean by an equilibrium point. So the definition says a point A is said to be an equilibrium point, point A is said to be an equilibrium point of point P if when P, the particle P is released from rest at A. So let me while I am trying to write the definition, let me also show you with the diagram. So we are talking about, well, let me first finish this writing and then we can say. So release from rest at A, and then P is going to remains at A. Okay. So what I just wrote is the following. So suppose the point A is said to be a point of stable equilibrium if the particle P, when released at rest from A, it never moves from A. Or in other words, if it is if it is released from rest at a point close to the point A, then it is going to come back to A eventually, right? So let us call this point A minus delta 1, and this is the point A plus delta 1, right? So if it is released at a point close to the point A, let's say delta 1 distance from point A, then it is eventually going to come back to capital A, and in the meantime, in the transient time, it is going to oscillate around that point A. Notice that we have drawn the potential curve, the Vx curve versus x, right? And in this neighborhood picture, we can clearly see that the point A is the minima, is the global minima of the potential. It is the global minima of the potential. Okay, so that gives us the stable equilibrium. Okay, so just to write what I just said, so equilibrium points are the stationary points of the potential energy Vx. They are the stationary points which are the maximum and the minimum of points of Vx. Equilibrium points are the stationary points of the potential energy Vx, which are the maximum and the minimum points of Vx. Okay, so from the figure we can see that so basically we need to find the max or the min of the V. Now then we have seen that from this figure 1, so from this figure 1 we see the following. Suppose, so I am just writing what I have just shown in the figure. So suppose the point P at rest is at the minima x equal to A. We find that it receives an impulse. Suppose P at rest at the minima x equal to A, it receives an impulse J, right? So what I am saying is, if the particle is sitting at x equal to a, then it is not going to do anything. It is going to sit at that point. But suppose we give a push to the ball so that it starts to move away from that minima, then we see that the impulse is going to be the change in the energy. Is going to be the change in the energy. For an impulse j, the change in the energy is given by j over 2m. So j behaves as if this is the change in the momentum of the particle, right? So the impulse is the dimension of the impulse is that of the momentum, right? So change in the energy is j over 2m. So what we see is that the total change in energy, in energy of this particle p is going to be E plus delta E. Earlier the energy at point A was capital E. Now the total, the new energy is E plus delta E, right? So now the energy of the particle has increased, right? Which means due to the change in energy, due to this change in energy, the particle is going to exhibit some motion, right? So which means that it is going to oscillate. It is going to oscillate in the interval a minus delta 1 to a plus delta 1, and we see that as delta E goes to 0, the amplitude delta will be the maximum of delta 1 and delta 2, right? The maximum of delta, let me call this as delta 1, the right hand side be delta 2, will this amplitude, which is going to be the maximum, we define this delta to be the maximum of the left and the right amplitude, is going to go to 0. Then when that happens, then the position vector goes to x equal to a, right? And if this is the case, then we are talking about a stable equilibrium. Okay. So enough of stable equilibrium. Now let us try to mathematically analyze the motion of this particle around the stable equilibrium. So what have we got? So we are trying to figure out the approximate motion equation of motion for small oscillations about the stable equilibrium. Oscillations about the stable equilibrium. Okay. Intuitively we can understand that this motion is going to be periodic oscillations, right? So simple harmonic motion about the stable equilibrium, capital A. So how to analyze the system? So to do that, let us write the potential energy of the particle. So the potential energy of the particle is, let's say we are talking about the potential energy of the motion of the particle around x equal to a, right? So we see that the potential energy V of x is equal to V of a plus x minus a times V prime. So what have we done? We have done a Taylor series expansion. V of a plus x minus a V prime a plus half x minus a square V double prime a, and so on. So the point is that the point A is a point of stable equilibrium. So we get that V prime is 0 because it has to be one of the minimum or the maximum point. So point of stable equilibrium. Okay. And so we get that this is my total potential comes out to be V of a plus this quantity. So from energy conservation, we have that the total kinetic energy half mv square, the total kinetic energy, plus the potential energy, which is V of a plus half x minus a square V double prime A, and we have neglected the higher order term. We have neglected it. So now we have this total potential energy, and this is going to be capital E, right? And what we see is that this is, if we write this kinetic energy in the form half m x double dot square plus V of A, so V of A plus x minus A square by 2 times V double prime A, and this is equal to E. And now let us now start to differentiate. So what we will do is we will let me call this equation as 1. So we differentiate 1 with respect to let's say x. We differentiate, no, we are going to differentiate with respect to t, and we divide by x, divide by the velocity itself, right? Okay, so what are we saying? So half mv square, I think we made a tiny error here, half mv square. So this is going to be half m x dot square, not x double dot. So now we differentiate once more with respect to t and divide throughout by v. So we are going to get from 1 we are going to get the following equation, that this is m x double dot times x dot, that is v, so we divide by v, plus derivative with respect to t of this constant va is going to be 0, and then we have x minus a times v double prime a is equal to 0. We have differentiated with time, and now notice that this equation is nothing but the equation of motion undergoing a simple harmonic motion, right? This is the standard undamped oscillation, non-driven undamped oscillation, and we are ready to write down the period of this oscillation. Notice that the angular speed, the angular well, what we can further do, there is one more step. We can replace x by x minus a, and then we see that our equation of motion comes out to be mx double dot plus x times v double prime a is equal to 0, right? So that is what we have, and from here let us divide by m. So this is divide by m, and this quantity is our omega square, and my period t of the oscillation is going to be 2 pi by omega, which is going to be 2 pi by square root v double prime a by omega square. Okay, well, that's something v double prime a by m, so that is divide by omega. So that is, the period is 2 pi by square root m over v double prime a, which means that if we want to find the period of oscillation, we just find the second derivative of the potential at the point of stable equilibrium and then use this formula, right? So let us look at this derivation with an example. So the problem says that we have a particle of mass 8, it moves on the x-axis. It moves on the x-axis under the force field. Right? It moves, a particle of mass m moves on the x-axis under the force field with potential V, which is given by x times x minus 3 square divided by 3, right? And we need to show that there exists a single position of stable equilibrium. Stable equilibrium. Okay. One way to find the stable equilibrium is we are given the potential curve, we can draw this curve and find the minima, the global minima. The other way is we can differentiate twice and find the sign of the potential at the point of extrema or the equilibrium. So we'll do the second option. We take the derivative of v and we find that this is x square, well, this is going to be x square minus 4x plus 3 and v double prime is 2x minus 4. From the first, when we set this equal to 0, we get x equal to 1 or x equal to 3, and when we plug both these points, we get that v double prime 1 comes out to be minus 2 and v double prime 3 comes out to be 2. Since this is positive, we expect that x equal to 3 is the point of stable equilibrium. Okay, that's a standard second derivative test. So which means that all we have to do is we have to find, well, that is all we have to do, and we can also find the period if we want. To find the period t is 2 pi square root v double prime divided by 3 divided by m, right? So this is 2 pi square root m divided by v double prime 3, and that comes out to be well, that comes out to be 3, 2, and the mass is 8 here. So this is going to be 2 pi times square root 8 by 2, or this is going to be 4 pi. Okay. So that is how we analyze the motion of these particles undergoing a motion around the stable equilibrium. Okay, so similarly we can look at this system for in 3-dimension space. What happens in 3-dimension space? So energy conservation, let us generalize energy conservation in 3D. So what we have is, if the particle P executes 3D motion, then moving from point A to point B along, let's say along a path C. So we are talking about a path in 3D space. The path C is going, then what we have is, then by energy principle, the energy principle, we get that the change in the kinetic energy TB minus TA is going to be integral from TA to TB, which is times F dot V dt. Okay, so TB minus TA, which is equal to the following. Okay, so what we have is that so from here we can quickly do a little bit of simplification. F dot V dt, so V is dr dt. So then when we plug this thing, we see that the integral comes out to be integral TA. So now instead of t, we will have the variable r. So this is going to be Ra to Rb f dot dr. Okay, f dot dr, because the variable now for integration is t, not t but r. So we have that the change in the kinetic energy is equal to this path integral from A to B, which is the work done. This is the work done by the particle in 3D moving from point A to point B. Right, so point A to B. I would not say Ra to B, but from point A to point B. Okay. So so that is what we have in terms of definition of the that is what we have for the energy principle in 3D. So let us continue our discussion. In fact, well, let me introduce some more terms. This question we have talked for some time now regarding the conservative field. This question is how to find such a field in general in 3D. See, in 1D the problems are simple. right? In 3D, we must have that F must be equal to negative grad V. If we can find a scalar potential whose negative grad is this vector force F, then we expect a conservative force field. Okay. So that is the 3D equivalent of the 1D formula that we have been solving so far. So let us look at the problem. We have, again, the definitions remain the same. This is F is a conservative force field, V is the potential energy, and so on. So let us look at this idea with an example. So the problem says show that F1, which is given by 2xi minus 2yj minus 2zk is a conservative force field, but F2, which is yi minus xj is not, right? Okay. So what we have is that F1, so let us look at the first force field. So we want to show the idea is that we want to show that F1 is negative grad V for some scalar V, right? Or if we look at this equation component wise, notice grad V is going to give us a vector, and that is equated to F1. So we equate component wise. So minus 2x is equal to minus dv dx, and then minus 2y, the y component is minus dv dy, and minus 2z is minus dv dz. From here we get that v of, it will have three variables, so v of xyz is x square plus some function of yz, and from the second one we get that this is going to be y square plus some function of xz, and let me call this as a function g, and finally we get, in the third equation we get that this is z square plus h of xy. Okay. So what we have is that so we want to find a single valued v. That is our goal, right? And we want to find such that all these three equations are satisfied, and that can only happen when v of x, y, z is x square plus y square plus z square, and we have a, and that's it. So we can all check that the derivative of v with respect to x and a minus sign is going to give a minus 2x, and with respect to y will give a minus 2y, and with respect to z will give a minus 2z. So that is the potential we were searching, and hence F1 is conservative, that is shown. Now the second part is we look at F2. Again, F2 we need to equate it to negative grad V. We want to find a scalar potential such that its negative grad is equal to F2, which means that we match each of the components. We see that negative dv dx comes out to be y, and negative dv dy comes out to be minus x. Okay. So now we start to integrate this, and what have we got? So we have got two equations. Well, the third equation will be negative dv dz is equal to 0. Right, now look at these two equations. If we differentiate the first equation with respect to y, so if we find what is negative v, so x y, so differentiate dv dx with respect to y, we are going to get 1. And on the other hand, if we differentiate this one v y x, this is going to be minus 1, right? Let me put the minus on the other side. So we have this. Now what we have got here is that vxy is not equal to vyx, or the mixed derivatives are not equal. So this is a sure shot sign of not getting a potential, that there does not exist a potential, if we can show that the mixed derivatives, when we change the order of the derivatives, they are not equal, right? So readers, the listeners, if we want to find a non-conservative force field, check whether a force field is non-conservative, we just need to figure out what are the mixed derivatives. Are the mixed derivatives equal or not? If they are equal, then rest assured we can find a scalar potential. If they are not, then there won't be any scalar potential. Okay, so that concludes this example. This question, we can proceed a bit more. In the first example with the scalar potential, we can even find the work done by the system. The work done by the system is going to be integral f dot dr. F is already given, and we see that this is also going to be minus 2x dx plus minus 2y dy plus minus 2z dz. Okay, and this is nothing but Vx. This is going to be nothing but minus Vx. This quantity is minus Vy, and this quantity is minus Vz, which means these are the individual derivatives of the scalar potential. And we see that this is going to be negative integral Vx dx plus Vy dy plus Vz dz. And this is a perfect, or this is an exact integral, and this integral is negative of dv, and which means from, let's say, point 1 to point 2, and this is going to give us that this is v of at point 1 minus v at point 2, and we find that this is also equal to so what we have found is that the work done by a conservative force field only depends on the end points 1 and 2. It never depends on the path. So the work done was, to begin with, was a path integral, but what we ended up was the integral boils down to just the values of the potential evaluated at the end points. Okay, so that is also a special thing about conservative force field. So let me just well, we do have some examples. Yeah. So let us look at one example, a quick example. The problem says show that f given by minus mgk, the projectile force field, is conservative with potential v given by mgz. And we show that the second part of the problem says show that the force field of the form f of r, of the form which is given by h of r times r hat, that is the radially directed force field, is conservative with potential v of r given by negative hr, where we have that hr is integral hr dr. Okay. So what have we got? So we have the first part is quite easy. In fact, we have already shown that the projectile force field is conservative and the potential is mgz. So I am going to leave it to the listeners to figure out the first part. The second part is a bit more curious case, where we haven't specified the form of the function hr, right? So let us now find what is grad v. So let us now find what is the part b. Let us find what is negative dv dx. So negative dv dx is negative dv dr times dr dx, right? So negative dv dr is dr. Well, I think the starting point could be well, let us not start from this point, otherwise we might get lost. The other way is we start the opposite end. So let us find dh dx. So what is dh dx? So dh dx is dh dr chain rule times dr dx. So so dH dr is nothing but H prime r, right? And so what is there? So this is H prime r, and notice that how is capital H defined? Capital H is the integral, it's the antiderivative of small h. So this is going to be H of r, H prime is capital H prime is H of r, and dr dx is going to be well, so r typically is square root of x square plus y square plus z square, and if we want to find dr dx, we see that this is equal to x divided by x square plus y square plus z square under the root, and this becomes x over r. So this quantity becomes x over r. Okay. So similarly, we can find that dH dy is going to be hr times y over r, and similarly dH dz is going to be hr times z over r, right? And which means that negative grad of h, the negative grad of negative hr. Why? Because we already have a negative hr, we want to take a negative grad, right? And we see that this is going to be grad of hr, and we see that this is also equal to hx I hat plus hy j hat, that is each of the component hz k hat, and we see that this is equal to hr times all these components x I hat plus y j hat plus z k hat divided by r, and the quantity in the numerator is also r. So r divided by r, and we get that this is hr, and I think we are already there. We see that negative grad of this quantity is hr, or this is our f, the force fr. So what we have found is that, which means that the potential V was minus hr. So regardless of the form of the function capital H or small h, we see that all the radially directed central fields or the central fields are conservative force fields. So this is a very powerful statement, the second part of this problem. Okay. So I think we are going to wrap up this particular discussion, and in the next discussion we are going to talk about we will talk about continue our discussion again on the central force field, and also look at the revisit the problem of simple pendulum. So thank you so far for listening.